So last meeting, we answered up to number 3 for torsion. So today, we'll continue with problem solving, starting with number 4. So number 4, the figure shows a steel shaft of length 1.5 meters and diameter 25 millimeters that carries a distributed torque of intensity, which is torque per unit length of P equals T sub B times X over L, where T sub B is equal to 200 Newton per meter, or 200 Newton meter per meter. Determine letter A, the maximum shear stress in the shaft, and letter B, the angle of twist of the shaft. Use G equals 80 GPa for steel. So first things first, we'll write our given. This is number 4. Okay. So given length, diameter, and torque. $25 millimeter. And then torque intensity of PB. So torque intensity, let's call that small t. TBO times X over L. For TB has a value of 200 Newton meter per meter. So you might be wondering why aren't we canceling the meter? Well, again, this is torque per length. So unit of torque is Newton meter, unit of length is meter. So that's why Newton meter per meter, torque per length. Okay, so and then G is 80 GPa. Okay, let's start with letter A. Okay, we're looking for maximum shear stress in the shaft. So first things first, we need to isolate your shaft. Okay, so you can do it this way. So here, at this part, there's a reaction. So reaction at A. So since our applied torque is this way, again using right hand rule, okay, that would be like this, right? So that is directed to the right. So this is your T. Let's use blue. Again, right hand rule. You have your fingers this way, and then your thumb will be facing that way. So its direction is to the right. And then reaction. So I'm just gonna guess. The reaction would be this way. Okay, so in contrast to that. So this is, let's call this TA. Okay, since this is the reaction at your support. And then again, using right hand rule. So your fingers curl this way, your thumb will be here. So this is the direction. And then next, use your equilibrium equation. Summation of moment equals 0. So negative TA plus T equals 0. Therefore, TA equals T. And T is TB times X over L. Now, to get the value of that, sorry, instead of TBX over L, okay, T is torque per length. So we're gonna get the summation of your torque times differential lengths. And to get the summation of that, you'll use integral calculus. So integral of t dx. And then from 0 to total length L. So from 0 here to total length here. Okay? And then let's sub in our value. T is TB times x over L. Again, from 0 to L. Next, we're gonna factor out the constants. So in this case, TB over L is constant, right? TB has a value of 200, so that's constant. And then length also has a value of 1.5. So I can rewrite this as TB over L dx. TB over L integral of x dx from 0 to L. Can anybody give me what's the integral of x dx? Call your integral calculus. What's integral of x over x dx? Correct, Shear? Yeah. Anyone else? Correct, Nina. Flores. Okay. So, Flores Gutierrez. Correct, it's x squared over 2. So this is TB over L, x squared over 2, and then evaluate from 0 to L. And then that is TB over L, L squared over 2. So we can factor out 2, right? So this becomes T sub B over 2L. And then L squared minus 0 squared. Okay. And then finally, this is just TB, T sub B over L cancels out 2 times L. And then just sub in our values. TB is 200 Newton meter per meter over 2. And then our length, make sure uniform units, so it's in meters, so 1.5. Please solve. What's the answer? Correct, Trinity? And Nina. It's 150. So this is your total torque or reaction torque at the support. So the unit there is Newton meter. Now, why did we get that? So for a torque distributed this way, to get the maximum shear, you need to get the maximum torque. And the maximum torque would appear at the support. Okay? Because as you can see, this is the equation for your distributed load, right, over L. So the larger your L, the smaller your torque will be. That's why this portion, it's the greatest. So now that we have torque, we can compute for shear stress, maximum shear stress. So this is still a rod. The answer or the equation for a rod is 16P over pi d cubed, right? So 16 and then P is 150. The unit here is Newton meter. So remember our standard unit for stress is MPa, so that's Newton millimeter. So I'm gonna multiply this by 1,000 to convert meter to millimeter. Okay. So 1,000 millimeter, 1 meter. So you know the conversion that I'm doing, and then over pi, diameter is given 25. So pi times 25 cubed. What's the final answer? Correct, Sierra. Gutierrez. And then correct Trinity. Okay. So it's 48.89. And then since our units are all in Newton millimeter, the stress is in MPa. Okay, so that's for part 1. Next, for part 2. So you might be tempted to use PL over JG and your T is 150. Okay, that's incorrect. Since here at every portion of your rod is experiencing torque, right? This TA is just the torque at one specific location, okay, the maximum torque. So to get the total angle of twist, we need to get the summation of the angle of twist per segment. Okay, so that's why it's not just 150 times L over JG, okay? So in order to do that, so let's isolate again another method. So this is still the same. There's still EA over here. Your torque is still here. And then the difference is we're gonna cut this at a distance from A. So this will be length X. Okay? And then cutting it at a section, there's gonna be an internal torque. So internal torque, again, assume distance. I'm gonna assume this way. So let's call that internal torque for AB. So now that we have that, we're gonna use again your equilibrium equation to relate all of these variables. Summation of moment equals 0. So let's use right hand rule to get the direction. So we already know this is to the left, this is to the right, and then this, again, using right hand rule, your thumb will point to the right. So you have negative TA minus T plus T plus capital PAB equals 0. And then therefore T for TAB is just TA minus T. Okay? So this TAB represents the torque for each distance X from the support. Okay? So that's why we're solving for TAB. So we're looking for torque at each segment. So minus T, to be more specific, TA is TBL over 2 or if we didn't simplify, that's TBL squared over 2L. Okay, so let's do that. TBL squared over 2L. Okay, so they're the same thing as TBL. And then minus, again, this is an intensity T. This torque should be multiplied by a distance to get its point load. So similar to a uniformly distributed load, right? We convert it first to a point load before we use it in our equation. So here, your torque intensity will be converted to a single torque. So again, that's integral of T dx, and then it's not from 0 to L anymore since we're only considering a segment. So instead of 0 to L, our maximum limit is X. Okay. And then just solve TBL squared over 2L minus T is TBX over L. So integral of T sub B. Again, from 0 to X. figure out your constants. So P sub B L squared over 2L minus, again, L is a constant, right? So I can factor that out as well as TB. So we got PB over L, integral of x dx from 0 to x. You already know x dx, right? That's x squared over 2 minus T sub B squared over 2 from 0 to x. Okay. And then I'm going to factor out 2. So P sub B L squared over 2L minus PB over 2L. Then sub x here. So we got x squared minus 0. Okay. And then finally, so x squared minus 0, that's just x squared. Simplify by factoring out the common terms or common variables. So both of them have PB over 2L. So the final equation would be PB over 2L. And then you're left with L squared minus x squared. Okay, so that's your equation for TAB. Now what? So now, we're going to use that in our equation for angle of twist. So again, remember, this is torque intensity. So again, each segment will experience an angle of twist. And we need to get the summation of each angle of twist of each segment. So we're going to use integral calculus again. So integral of the individual angle of twist of your differential members. So that would be, instead of PL, again, we're going to consider a very small segment. So instead of L, we're using dx. So T dx over JG. Okay? And then, let me draw that. Okay. We're using a differential length segment here. So this is your dx. And then it's running again from this side to this side. So that's from 0 to L. Okay. Total length L. This is your A, B. And now let's just solve. Let's sub in this equation here. So integral of PB. Okay, PB over 2L. We already know that to be a constant, right? So I'm just going to factor that out. PB over 2L, integral of dx, or integral of what's left, L squared minus x squared dx over jg. Again, from 0 to L. And then another thing, J is polar moment of inertia, right? And that's also a constant. That's a property of your object. So no matter where you take this segment, J is the same. So I can also factor out J. And then modulus of rigidity, or shear modulus G, is also the same. It's constant. It's the property of your material. So I can also factor that out. So you get G. So therefore, we're now only left with integral of L squared minus x squared dx. Okay, next step, let's solve. So AB over JG, integral of L squared dx is what? What's the integral of L squared dx? Considering L is a constant, so what's the integral of a constant times dx? No. Again, L is a constant. So integral of a constant. Okay, it's just x. So for example, integral of 2 dx. That's just 2x plus c, right? So just copy your constant and then the variable. So therefore, integral of L squared dx is just L squared times x. And then integral of x squared is x cubed over 3. And then evaluate from 0 to L. So you'll get TB over 2LJG. Sabihin L squared times L, you'll get L cubed minus L cubed over 3. And then when you sub in 0, the entire thing is just 0. Okay, and then let's simplify further. L cubed minus L cubed over 3, that's 2/3 L cubed. So finally, you get T sub B over 2LJG times 2/3 L cubed. Okay, and then cancel out L. Final answer or final equation before we sub in our values is 2 TBL squared. Now, 2 also cancels out. So TB, this becomes 2. L squared, and what's left is 3JG. Again, TB is 200 Newton meter per meter. And then meter just cancels out, so that's just Newton. And then length is 1.5. Okay, convert that meter to millimeter, so times. Okay, 1 meter is 1,000 millimeters, and then this is squared over 3. And then J, polar moment of inertia for a shaft, rigid shaft or solid shaft is pi d to the 4th over 32. So times pi. Diameter of this is given. It's 25. Just delete. So times 25 raised to 4 over 32. And then modulus of rigidity is 80. And then please solve. What's the answer? Just this. Solving just this. What's the answer that you get? Again, please solve. What's the answer? Nope. Again, remember this is squared. GPA. GPA convert to MPa times 10 raised to 3. Recompute. Okay, please recompute. Instead of 80, it's 80 times 10 raised to 3 because GPA convert to MPa. Okay, correct Trinity. Who else? Oh, 2 points ka na. So anyone else? Correct Jade. And who else? One more. Divide niyo lang ng 1,000. Yung sagot mo. Correct Audrey. Enrique. And then hold on to that answer because that's in radians. So you'll get 0.06 rad. Again, the answer for angle of twist should be in degrees. So times 180 over pi. What's the final answer? Is it 80 or 82? 80. Wait. 0.05 or 0.0488. That is 25. Yeah. Diameter is 25. Yeah, I wrote 24. That's why. So you should get 0.049 or 0.05. Then times 180 over pi. Compute. What's the final answer? Yeah, correct. 2.80 degrees. You got it. Correct, Trinity. Correct, Alona. And Moni. Okay, so wala pang 2 points, Santa Maria and Moni. .80 degrees. Okay. That's our final answer. Any questions for number 4? Please answer in the chat. Okay, since no questions, let's move on to the next problem. Number 5. There's no figure for number 5. A solid steel shaft in a rolling mill transmits 20 kilowatts of power at 2 hertz. Determine the smallest safe diameter of the shaft if the shear stress is not to exceed 40 MPa and the angle of twist is limited to 6 degrees in a length of 3 meters. Use G equals 83 MPa. So this is a bit different from what we did. In the past examples, we're looking for maximum shear stress and angle of twist. Here, we're given shear stress and angle of twist, we're looking for allowable force or allowable dimension. So just keep that in mind. First step is the same, write out your given. Rolling mill transmits 20 kilowatts of power. That's P for power. 20 kilowatts. 2 hertz. So that 2 hertz is actually the frequency. So that's your F, 2 hertz. Next, we're looking for smallest safe diameter. So we're looking for dimension. And then we have the limit, shear stress, 40 MPa. So allowable shear stress, 40 MPa. Angle of twist, 6 degrees. And then we have a length of 3 meters. And then G is 83 GPa, right? Okay, so what we'll do is we're going to solve for dimension for each restriction. So you can either start with solving for dimension using shear stress or angle of twist. So let's start with using shear stress first. The recall equation for shear stress is 16P over pi d cubed. I need to know P, which is torque. And recall in our lecture, to get torque from power, we have an equation. Specifically, torque is just equal to power over 2 pi f. Okay? Now, the standard unit for power is watts. This is in kilowatts, so convert that to watts times 10 raised to 3. Okay? And then 2 pi, standard unit of frequency is hertz, so no problem there, just copy your 2. Okay? Please solve. What's the answer? Correct, VMA? Who else? Correct, Audrey. 1591.55. This will be in Newton meter. Okay, if you use this equation, that's Newton meter. Since it's not a whole number, store this in your calculator. Next, again, using shear stress. Okay, shear stress is 16P over pi d cubed. Allowable shear stress is given 40 MPa. So 16. Our torque is in Newton meter. It should be in Newton millimeter since our stress is MPa. So convert that to millimeter. So 16 times P. So that's 1591.55 times 10 raised to 3 to convert meter to millimeter. Or I'll just write this again. 1 meter, 1000 millimeter. So you know this is a conversion factor. And then pi d cube. Please solve. What's d? Correct, Alona and Muni. Miguela, so Santa Maria and Muni. It's 58.74 millimeter. Okay, so that's one choice for D. Now, we need to check for angle of twist. Okay, because we have another restriction here. So angle of twist equals TL over JG. Now, angle of twist is in radians when we solve for this as is. So I need to convert this to radians. So 6 times, to convert degrees to radians, that's just pi over 180. So it's just the opposite. Okay? And then equals T. Again, that's in Newton meter. It should be Newton millimeter. So 1,000. And then length, 3 meters. So once again, 1,000 millimeter per meter. J, this is a solid shaft. So the equation for J is the same, pi d to the 4th over 32. So pi, d is what we're looking for, over 32. And then G is given, GPA convert to MPa. So that's just times 10 raised to 2. Please compute what's D. Correct, VMA? Who else? Correct, Vanessa. Okay, so 48.64 millimeter. Oh, this millimeter. Therefore, which should I use? 58 or 48? Okay, everybody, please try to answer. What should be our final answer here? The minimum diameter that we can use, is it 48 or 58? Correct, Tim? What the others? Please answer as well. What do you think? Is it 48 or 58? Okay, so let me put it this way. So this means your structure needs at least 58.74 so that it doesn't fail in shear stress, okay? Because this is the required diameter to carry the allowable shear stress. In the same way, this is the required diameter to not exceed your angle of twist, okay? So once again, this is the diameter that we need to not exceed shear stress. This is the diameter that we need to not exceed angle of twist. If that's the case, what should be our final diameter? Okay, correct, Vanessa. It should be, yes, correct. Should be 58.74. Why? If you get any lower than this, your structure will fail because this is the minimum required diameter. Okay, anything less than that, you'll get a stress greater than 40 MPa. Okay, so again, if you're kind of confused, okay, for force, the maximum force that you can get is the least number. Okay, if you're looking for maximum force that can be applied. For example, for torque, what is the maximum torque that can be applied? We're going to solve for each restriction, and then you're going to choose the minimum number. For dimension, however, is the opposite. You need to choose the maximum dimension. Okay, because again, anything less than that will cause your structure to fail. That's why final answer 58. Okay? Okay, so that's number 5. Any questions for number 5? Please answer in the chat. How about the others? Please answer as well. Okay. So that ends the topic for torsion.